the energy of an electron is related to its velocity. Kinetic energy is 1/2 mv squared. So the energy depends on the velocity. The velocity and the position are complementary, so the energy and the position are complementary. So if an electron has a given energy, then the best we can do is describe this region in which it is most likely going to be found. We can't say it's exactly here. It is not in a nice, predictable orbit going around the nucleus like the Earth goes around the sun. That's not what electrons do. That's an orbit. In quantum mechanics, we have orbitals. And so they're a little bit like an orbit in that it describes where the electron is, but they're very messy. It's just a region in which the electron is likely to be found. The properties of atoms are related to the energies of the electrons, and so the energy of the electrons is very important. Schrödinger, same Schrödinger of Schrödinger's cat. Schrödinger had an equation, and this allows us to calculate the probability of finding an electron with a specific amount of energy at a particular location in the atom. It doesn't allow us to calculate exactly, but it allows us to calculate the probability. So solutions to Schrödinger's equation produce many wave functions. So the wave function is given the symbol psi. And these wave functions describe the wave-like nature of electrons. If we plot psi squared, if we square the wave function, that's going to give us a representation of the orbital. So calculations indicate that the size, the shape, the orientation of the orbital are determined by 3 different integers. And these were added into this to quantize the energy of the electron. We know that the energy is quantized. We can see that in the emission spectra of different elements. There are only specific energies that are allowed. So we've got 3 terms in here that quantize the description of the electrons. These are called quantum numbers. So we've got the principal quantum number, given the symbol n. We have the angular momentum quantum number, that's L, and the magnetic quantum number, m sub L. There's a 4th number called the spin quantum number, and that's m sub S. So the principal quantum number n is an integer. They're all integers. This describes the overall size and the overall energy of an orbital. This would correspond to Bohr's energy levels. He had level 1, level 2, etc. N can be any integer starting with 1 and getting bigger, 1, 2, 3, 4, 5, etc. The larger the n, the higher the energy, and the larger the orbital size. So the orbitals get bigger and bigger, just like the orbits got bigger in the Bohr model. For hydrogen, we can use this equation and we can calculate the energy of an electron. So the energy of an electron is equal to minus 2.18 times 10 to the minus 18 joules times 1 over n squared, where n is that principal quantum number. That works for hydrogen. The energy here is negative because the electron's energy is lowered by its interaction with the nucleus. So if you were comparing this to an electron that is not attached to an atom, that might have a 0 or a positive energy. This is a negative energy because it's lower. Did you have a question? N is like the circles, yes. So in the Bohr model, we had the nucleus, and then we had orbits, right? And so this was 1, and this was 2. So this would be principal quantum number 1 and principal quantum number 2. And as the size gets, as the number gets bigger, the size gets bigger. but they're not actually orbits like that. Did that answer your question? As we get higher and higher with n, the energy difference between the orbitals gets smaller. I realized yesterday that, I guess that must have been last Thursday, I got it backwards. Not sure how or why, but I did. So if we're looking at the rungs on a ladder as representing the energy levels, as we go higher and higher, the levels get closer and closer together. And I got it exactly backwards last week. Thankfully, it's not a critical concept, but the levels get closer and closer. So here's an energy diagram. There we've got energy going up. Here's n equals 1, so the lowest principal quantum number. And we can calculate, this is for hydrogen, we can calculate the energy of an electron that is in this place with this energy with n equals 1. So it's going to be minus 2.18 times 10 to the minus 18 joules. If n equals 2, we can also calculate the energy, or 3 or 4. And these calculations are done with that equation, minus 2.18 times 10 to the minus 18 joules times 1 over n squared. So for this one, n is 1, and so the energy is the minus 2.18. And as we get up higher and higher, the energy becomes less negative. Negatives always make things hard to understand. So if we think about altitude, and 0 is sea level, right, at the surface of the ocean, these electrons are below the surface of the ocean. They would have negative altitude. If you think about potential energy, the farther you raise something up off the ground, the higher its potential energy. So here it's just that we're starting at the bottom of the ocean floor, and we're lifting. As you go higher and higher, the energy becomes higher, although the altitude is still negative. Does that make any sense? Because if you drop a rock in the ocean, you're halfway down and you drop the rock, it still goes down, right? It still has some potential energy. The next one is called the angular momentum number. This is an integer that describes the shape of the orbital. And L can be any number from 0 up to 1 less than n. So whatever n is determines how many different values L can have. Each value of L is also given a letter that we associate with the shape of the orbitals. And these letters came from descriptions of the lines in emission spectra. Principal, diffuse, fine, and I always forget what S is. So if L is 0, we call that an S orbital. L equals 1 is P, 2 is D, and 3 is F. I know you'd like that to be A, B, C, D, but it's S, P, D, F. We'll get used to it. The magnetic quantum number, m sub L, specifies the orientation of an orbital. What direction is it pointing relative to the other orbitals? M sub L can be anywhere from negative L to positive L, including 0. So if we had a situation where we had L is equal to 2, then m sub L could be anywhere from negative L, negative 2, all the way up to positive L, positive 2, and all the integers in between, including 0. So then there's 5 different integers. So this describes 5 different orbitals, and they're arranged differently in space around that nucleus. And then the spin quantum number. So this describes the orientation of the spin of the electron. Electron spin is a property that electrons have. Thankfully, we do not have to understand exactly what that is. They all have the same amount of spin, but it has a different direction or orientation. So it's not spinning like a top, but we can think of it that way because it's easier, and it's not going to hurt anything. Did you guys ever play with Beyblade tops? Yeah, my son Andrew really likes Beyblades. There's ones that spin counterclockwise and there's ones that spin clockwise, right? So there are electrons with a positive spin and a negative spin. Spin up, spin down. This quantum number is either plus 1/2 or minus 1/2. And so you can think of it as counterclockwise or clockwise spin of the electron. So to describe an orbital, we need those first three quantum numbers. A combination of n, l, and m sub l will describe one orbital. So if n equals 1 and L equals 0 corresponds to an S shape. And if L is 0, M sub L can only be 0. So this describes the 1s orbital. There's only one 1s orbital. If we're looking at different orbitals that have the same value of n, those are said to be in the same principal level or in the same principal shell. And orbitals with the same values of n and l are said to be in the same sublevel. So there's levels and there's sublevels. So here's a diagram. So n equals 1. When n equals 1, the only possible value for L is 0. Because L can be 0, 1, 2, 3, up to 1 less than n. Well, 1 less than n is n equals 1 is 0. So all we can have is L equals 0. L equals 0 corresponds to an S shape. So there's one sublevel, it's S, and there's only one orbital in there. There's only one magnetic quantum number. So there's only one orientation. We go up to the second energy level, principal level. Now we have two possible values for L. 0, which corresponds to S, and 1, which corresponds to P. For L equals 0, again, M sub L can only be 0. There's one S orbital in that second level. When L equals 1, M sub L can be negative L up to positive L. So it could be negative 1, 0, or positive 1. So there are three different 2p orbitals, and they are aligned differently in space. We'll see pictures in a minute. Third level, now we can have L equals 0, L equals 1, or L equals 2. So these are very similar to the ones down here. When L is 2, then M sub L can be minus 2, minus 1, 0, 1, or 2. 5 different possibilities. So there are 5 orbitals that are 3D. Those are sort of nice generalities. You can read that. So we should be able to do things like this. List the quantum numbers associated with all of the 5D orbitals. How many 5D orbitals exist? Okay, so 5D. What does the 5 tell us? N. So N equals 5. And what does the D tell us? So that's L. L equals 0, 1, 2, 3 would be S, P, D, F. So 5D means that L equals 2. So we've got N equals 5 and L equals 2. Okay, so the next one, M sub L, what are the possible values for that here? Yeah, negative 2, negative 1, 0, plus 1, plus 2. So how many 5D orbitals exist? 5 of them. 1, 2, 3, 4, 5. So we've got 5 orbitals. Not because of the 5 here, but because of the d. So each orbital has its own set of quantum numbers. So if we show this as n and L and m sub L, we've got 5, 2, and negative 2. We have 5, 2, and negative 1, 5, 2, and 0, 5, 2, and plus 1, 5, 2, and plus 2. It's kind of like a code, or an identification system, or a VIN number on a car, right? Each orbital has its unique set of quantum numbers. Here's another thing, yeah. Each set of quantum numbers is supposed to specify an orbital. However, each set contains one quantum number that is not allowed. Replace the quantum number that is not allowed with one that is allowed. Well, let's look at A first. So n equals 3. Is that possible? Sure. So based on that, n is equal to 3. Could L be equal to 3? Nope. L could be 0, 1, or 2, but it can't be 3. Okay, so it can't be 3. We got 0, 1, or 2 to choose from, but there's only one that's messed up. M sub L is plus 2, so that means that L has to be what? It has to be 2. Because if it was 1, then this one wouldn't be allowed. Or if L was 0, this wouldn't be allowed. Let's look at this one. N equals 2. Well, that's fine. L equals 1. Does that work with n equals 2? Yeah, it's fine. M sub L is minus 2. Does that work? No, because M sub L is minus L up to plus L. Minus 1, 0, or 1 for L equals 1. Now, is there a restriction on which one of those three we choose? No. I'm going to pick 0 because it's a nice round number. Could be minus 1 or plus 1. ML starts with negative L. So here, well, it doesn't really start. There's just different possibilities. So it could be minus 1, 0, or plus 1. We just need to pick one that is allowed to answer this question. There are 3 different ones that are allowed. So we could also have 2, 1, and minus 1, or 2, 1, and plus 1. Those are also valid. What about this one? N equals 1. Can L equal 1? No. What would L have to be? 0. Because it can only go up to 1 less than N. Any questions? Yeah.
It's actually like the one before that.
Okay.
So yeah, we got like 5, right?
Mm-hmm.
Possible.
Yeah.
Would we also count the spin, quantum spin, or is that?
We'll get to that. The reason that the spin thing describes electrons in the orbitals. And what we'll see is that there can be 2 electrons in one orbital. So yeah, there are 10 different combinations there, including the spin. Yeah. Atomic spectroscopy explained. So each wavelength that we see in the atomic spectrum corresponds to an electron transition between 2 different orbitals. Orbitals have a specific energy. The atom absorbs energy, the electron gets excited to a higher energy orbital. It's not stable up there, just like something balanced on the roof of the building isn't stable, right? It's high potential energy. the electron's eventually going to fall back down to a lower energy orbital. When it does that, it releases energy because it went up because it absorbed energy. What goes in has to come out. The energy gets released as a photon of light. And the energy of that light is equal to the difference in energy between the two orbitals where the electron is transitioning. So here we have electron in the first energy level. That's the lowest one. That's going to be the most stable. We zap it with some sort of energy. The electron absorbs energy, jumps up to n equals 3. That's a higher energy level. It can go up there, but it's not stable. So it's going to come back down. As it comes back down, it has choices, like an electron can choose, right? It could go different places. It could go to n equals 2, or it could go all the way to n equals 1. But it has to go to one of the lower principal levels. When it goes back down, then it releases light energy, and that energy corresponds to the difference between n equals 3 and n equals 2. So by looking at the colors of the light, we can measure their wavelength. From the wavelength, we can calculate the energy. We can know the energy difference between the levels in an atom. In order to go to a higher energy state, the electron has to get the correct amount of energy. It will only absorb the right amount of energy. It's not going to take in any extra. The right amount of energy is the difference between those two states. The high energy state is unstable. It'll go down to a lower energy state, and the line in the emission spectrum corresponds to the energy difference between the two energy states. Hydrogen is great because we can actually predict and calculate things for it. So the wavelengths of the lines in hydrogen's emission spectrum can be predicted by calculating the difference in energy between two states. So we saw that equation, E equals negative 2.18 times 10 to the minus 18 joules times 1 over n squared. So we can use that to calculate the energy difference between two levels. So the Bohr model predicts this well. The quantum mechanical model also predicts it well for this one electron system. So both of them work for hydrogen. So here's how that calculation would be done. So the change in energy is equal to the energy of the photon. That's going to be equal to the energy of the final state minus the energy of the initial state. The change in energy. So the final state would be minus 2.18 times 10 to the minus 18th joules times 1 over nf squared. And then you subtract the energy of the initial state. So that's got the initial n squared. You can factor out the 2.18 number, and you've got 1 over f squared minus 1 over I squared. So the change in energy for the atom is going to be equal to the change in energy for the photon, but the sign will be opposite, because if the atom loses energy, then the photon gains energy, right? So one's going to be positive and one's going to be negative. And we also have this relationship. The wavelength is equal to hc over the energy. We saw that earlier as E equals hc over lambda. If we know the energy, we can calculate the wavelength. So there was a pre-lab question that had to do with transitions between different energy state or different principal shells. And so I think it asked which one would be bigger. Is that what it asked? Orange and yellow. Okay, so it gave you colors and asked which would correspond to the biggest energy change for that electron transition. So the biggest energy change, you can calculate the energy using the wavelength. Now they didn't give you a wavelength, but you can look at the chart and see which is higher in energy or which is higher in wavelength, right? And so if we just think about it, Roy G. Biv, after violet is ultraviolet, that's the high energy end. So orange or yellow is higher in energy, right? So that's going to be a larger difference, and that's going to be a bigger change between NF and NI. So if you had to choose between, say, 3 to 2 and 5 to 2, which of these is going to have a bigger energy difference? The 5 to 2, because you're actually skipping some levels. You're going 5, 4, 3, 2, you're jumping all the way down to 2. This is going to be a larger energy difference. So that would correspond to light being emitted with a higher energy.
So you mean that's the N for the violet will be the same, and then the N initial is what the energy is?
Well, you could have the initials be the same and the finals be different. It just has to do with the difference in them. But that should give you enough information to answer that question.
Three colors of
Orange, green, and yellow. So basically it's asking you which of those has the highest energy. Because the highest energy is going to be the biggest change in N.
So we can be energy
Yeah, so if you're thinking of the Bohr model, right, you've got N1, N2, 3. So this change is going to be bigger than that change, right? And this change is going to be even larger. So you can't get the exact which N is it from the color of the light, but you can say, well, this one is a larger transition than this one because you look at the energy of the light that's given off. Oh, well, instead of drawing my ugly picture, we could have looked at this. So this is for hydrogen specifically. So if we take hydrogen and zap it with enough energy, we can actually turn it into an ion, and that would be sending that electron to a level of n equals infinity. It completely left the atom. It's no longer in the building. But what if we don't shoot it all the way out? Maybe up to level 5 or 4 or 3. And then we can look at the transitions as it returns to the ground state. So transitions from 5, 4, and 3, and 2 all the way down to 1, those are really large transitions. Those are going to be in the ultraviolet region. We can't see those with our eyes. We can see these going down to level 2 from 5, 3, and 4. 5, 4, and 3. So these transitions correspond to energy, light energy that is within the visible region. And so we are going to observe those 3 lines today in lab. Up here, if we're going from 5 to 3 or 4 to 3, that's a smaller energy transition. That energy is lower than visible light. That's in the infrared region. And so we can't see that either. But there are 3 of them that we can see. Okay, determine the wavelength of the light absorbed when an electron in a hydrogen atom makes a transition from an orbital in which n equals 2 to an orbital in which n equals 7. So we've got two n's. One's initial and one's final. Which is the initial? 2 is where it starts. So it's going from n equals 2. So this is the initial. And it's going to n equals 7. So this is the final. So we're supposed to determine the wavelength. Well, we had this equation that the change in energy is minus 2.18 times 10 to the minus 18 joules. Correct me if I get anything wrong here. 1 over nf squared minus 1 over ni squared. If you get your final and your initial mixed up, you'll just end up with the opposite sign. Because the amount of energy to go from the bottom to the top or from the top to the bottom, the difference is the same, it's just the direction. So we could calculate the energy of the light, and from the energy we could calculate the wavelength. So this is minus 2.18 times 10 to the minus 18 joules. The final is 7. 7 squared is 49. Minus the initial, 2 squared is 4. So we do this negative 2.18 EE minus 18 times parentheses 1 divided by 49 minus 1 divided by 4, close the parentheses, enter. So the change in energy is equal to 5.01 times 10 to the minus 19 joules. The wavelength is equal to hc over the energy. So h is 6.626 times 10 to the minus 34 joule seconds. C is the speed of light, 3.00 times 10 to the 8th meters per second. And then in the bottom, we've got 5.01 times 10 to the minus 19 joules. We can look at our units. The joules cancel out, the seconds cancel out. We're left with meters. So we got 6.626 EE minus 34 times 3 EE8 divided by 5.01 EE minus 19. It's a really small number. 1, 2, 3, 7. 3.97 times 10 to the minus 7 meters is the wavelength. Any questions?
So those two top ones, the speed of light, that doesn't change at every point, it doesn't change.
Yeah, H and C are constants. H is called Planck's constant, and it's always this if you use those units. And C is the speed of light, 3 times 10 to the 8th meters per second.